everyone, I am Professor Anish Vora and I welcome you all in this video lecture. Before we study oscillators in detail, it is very important to understand the LC tuned circuit, which is also known as a tanked circuit. With the help of L and C, we can generate oscillations, and that is what we require in the oscillator. Let us revise our knowledge about oscillator. Oscillators are circuits that generate a continuous voltage output waveform at a required frequency with the values of the inductor, capacitor or resistors forming a frequency selective LC resonant tank circuit and feedback network. This feedback network is an attenuation network which has a gain or feedback factor less than 1. We know that beta is always less than 1 and starts oscillation when product A dot beta greater than 1, which returns to unity A beta is equal to 1 once oscillations commence. So that is a very essential condition for the sustained oscillations, that A dot B product is equal to 1. The LC oscillator frequency is controlled using a tuned or resonant inductive capacitive LC circuit, with the resulting output frequency being known as a oscillation frequency. By making the oscillator's feedback a reactive network, the phase angle of the feedback will vary as a function of frequency, and this is called phase shift. In case of oscillator, we require positive feedback. We have different types of oscillator. Sinusoidal oscillators. These are known as a harmonic oscillators and are generally a LC tuned feedback or RC tuned feedback type oscillator that generates a purely sinusoidal waveform which is of a constant amplitude and frequency. While we have different type of oscillator, that is a non-sinusoidal oscillator, these are known as a relaxation oscillators and generate complex non-sinusoidal waveform that changes very quickly from one condition of stability to another, such as square wave, triangular wave or sawtooth wave type waveforms. When a constant voltage but of varying frequency applied to a circuit consisting of an inductor, capacitor and resistor, the reactance of both the capacitor resistor and inductor resistor circuit is to change both the amplitude and phase of the output signal as compared to the input signal due to the reactance of the components used. At high frequencies, the reactance of a capacitor is very low, acting as a short circuit, while the reactance of the inductor is high, acting as an open circuit. At low frequencies, the reverse is true. The reactance of the capacitor act as an open circuit and the reactance of the inductor act as a short circuit. Between these two extremes, the combination of the inductor and capacitor produce a tuned or resonant circuit that has a resonant frequency in which the capacitive and inductive reactance are equal and cancel out each other, leaving only the resistance of the circuit to oppose the flow of current. This means that there is no phase shift as the current is in phase with the voltage. Now let us understand LC tuned circuit. We have one inductor, that is L, and one capacitor. Both are connected across each other, that is a parallel circuit. And initially it is connected with the power supply also. We have a switch which can change the position. Either it can be connected to P or it can be connected to R. When it is connected to P, the capacitor is connected across the power supply, and when it is connected to R, it is connected across the inductor L. So parallel L and C, that is known as a LC tank circuit or LC tuned circuit, and which is responsible for generating the oscillations. Now initially switch S is connected with the P, meaning is capacitor is connected across a DC power supply. As soon as the switch is connected across the power supply, the current start flowing from the power supply to the capacitor, and capacitor start charging. Capacitor charge with the polarity positive on the upper plate. So at that time we have output voltage that can be increasing sinusoidally from O to point J. When capacitor is fully charged and when the peak voltage, that is equal to the supply voltage at point J, the switch is interchanged from position P to position R, and then power supply is disconnected from the capacitor and capacitor is connected across the inductor. Capacitor and inductor both are energy storing device, both are passive component and both stores the energy. Capacitor stores the energy in electrostatic form and inductor stores the energy in electromagnetic form. So as we discussed, when capacitor is fully charged, it is disconnected from the power source and switch is now connected to R. Now capacitor and inductor both are connected parallel to each other, and as soon as the connection is made, the current start flowing from the capacitor to inductor. So initially when capacitor was charging, we had an output voltage waveform from O to J. Now during the current flow from capacitor to inductor, we have slowly voltage discharging from the capacitor and the waveform, that is from J to point K. When capacitor is fully discharged, the output voltage waveform comes to zero level, that is point K. When energy is transferred to the inductor, capacitor has no energy at all now. It is fully discharged. Energy is now stored in the inductor in the electromagnetic form, and that is a property of the inductor to maintain the current in the same direction. So even if capacitor fully discharged, the flow of current is maintained in the same direction, and then the energy start transferring from the inductor to capacitor. Capacitor start charging with the reverse polarity. So if current is maintained in the same direction, now capacitor charge but with the positive polarity on the bottom plate. So during this process we have output voltage waveform, that is from K to L. The current direction is maintained constant, but now the charging of the capacitor, that is in the reverse polarity, reverse direction. So voltage waveform, that is from K to L. When capacitor is fully charged, we can say that the energy is transferred from inductor to capacitor. And then the direction of the current change. Now it will start again from the capacitor to inductor, and then we have an output voltage waveform that is from L to M. When again capacitor is fully discharged, it will come to zero level voltage, that is point M. And same cycle repeat again and again. So at every half cycle, energy is transferred from capacitor to inductor, and in the next half cycle, it is transferred from inductor to capacitor. This process remains continuous, and then we have oscillations, sinusoidal oscillations in the output voltage waveform. Desired frequency, that is a resonance frequency, can be achieved by appropriate selection of value of L and C. Now let us understand the damped oscillation. We know that initially we connected capacitor across the power source and it was fully charged, and when capacitor was fully charged, the power source was disconnected from the LC circuit, and then LC circuit has no external power source. So during transfer of energy from capacitor to inductor and inductor to capacitor, at every half cycle we have oscillations in the output voltage, but the amplitude of the output voltage goes on decreasing, because without external source of energy, at every half cycle during transfer of energy from inductor to capacitor and capacitor to inductor, we have certain amount of loss in energy. So eventually the amplitude of the output voltage goes on decreasing, and ultimately it becomes zero when entire energy is wasted and there is no energy left to maintain the current. And then output voltage waveform comes to zero level. So this type of output is known as a damped oscillations. When we need a sustained oscillations, we have to supply sufficient energy externally equal to the loss of energy in each half cycle. Then we can have a sustained oscillations. So this is all about LC tank circuit. Thank you for watching my video. Keep watching. Thank you very much.